we'll continue with the talk by Raju Venugopalan, the Pomeron past, present, and future.
Yeah, thank you very much. It's great to be here. When I suggested this title, I realized that maybe I was chewing off more than I could handle. But anyway, we'll see where this goes. So in this collaboration, my interest is in connecting all of these ideas to phenomenology. In particular, what's shown here is a high multiplicity proton-proton collision. So these are a very large multiplicity of particles that you see in a single proton-proton collision that's triggered on such high multiplicities. And you see very interesting structures in there, such as long-range correlations, azimuthal collimations, and so on, that are really very interesting to understand. In general, my interest is in constructing effective field theories to understand data from collider experiments at Regge, LHC, and in future at EIC. So I just want to make some preliminary remarks to sort of situate this talk. So there's, of course, a vast pre and post QCD literature on a Pomeron, which dating to more than 60 years, and it's impossible to survey this in this talk. And in preparing this, I had this thought that I don't mean to blaspheme, but Pomeron is a kind of God particle in a certain sense, that no one really knows what it is, but people have very differing ideas on what it is. And it's not clear it's a robust concept in QCD, but it's endlessly fascinating. So one can continue talking about it. And in fact, at some, not so long ago, it was kind of a dirty word until it was kind of resuscitated. And it's sort of its essential fascination kind of reemerged. I've also not discussed this very interesting literature on the Pomeron and holography. There are many experts in this room who know much more about this than I do, and I would certainly be interested in learning more. And I think one of the interests would be to sort of connect this to what I'm going to talk about. And so my perspective is therefore a very narrow one, but hopefully of interest in particular with regard to matching non-perturbative approaches to the UV. So some of the non-perturbative approaches that we talked about, for instance, which is also kind of the concluding slide in the previous talk. And so to further situate what I'm going to talk about, so this is kind of the landscape of the strong interactions in QCD. Of course, asymptotic freedom, great success of it. So on the y-axis, we have the resolution in Q squared. So if you think of deeply inelastic scattering. And on the x-axis, you have the parton density, which grows as the momentum fraction of the partons gets to be smaller and smaller. So increasing energies on this axis. And so at very high resolutions, of course, we have asymptotic freedom. We have a description in terms of quarks and gluons. And then as you go down in resolution, the physics becomes more and more non-perturbative. You have, of course, the description of the hadrons, is these outstanding problems that we're interested in. And as you go sort of at higher energies, at fairly low resolution, which is kind of the situation with experiments until more recently, you had this kind of effective descriptions emerging in terms of Pomerons and Regge trajectories. Now, however, with the large phase space that's opened up with colliders, you can ask kind of interesting questions about this larger parts of this landscape, where you can think about in terms of a kind of a condensed matter regime of QCD, where you start to see strongly correlated quark-gluon dynamics. So now, in the early days of QCD, this was also kind of a dirty word, but now you can sort of turn it around and say, what are the many body properties of quarks and gluons as you go along this landscape, where, we have these beautiful evolution equations, and when do they sort of break down? And what I'm going to argue to is that there's a very interesting regime there, which sort of sits between weak and strong coupling, which corresponds to very high parton density gluon matter. And that, because it's accessible in weak coupling, may offer you a different path to sort of thinking about these objects here. But let me mention some words about the Pomeron, since that's in the title of my talk. So the total cross section. So the remarkable thing about the Pomeron was that, which continues to be fascinating, is that total cross sections across many orders of magnitude, all the way from SPS energies to the LHC, are simply described in terms of these Pomeron and Reggeons trajectories. So if you think about hadron-hadron scattering at high energies, where S and T are the Mandelstam variables as shown here, there's a factorization of the scattering into so-called impact factors. And then there's the T-channel exchange of this object here with some characteristic parameter alpha of T, which can be understood as the Regge trajectory. So, and the scattering amplitudes to be parameterized in terms of S and T as S to some power of alpha of T, where alpha for the Pomeron would be reach up to unity plus corrections, and alpha prime would be sort of the object that corresponds to the string tension. And so this very simple picture came from the idea from Regge theory, where you thought of this T-channel exchange as a pole in the TJ plane with vacuum quantum numbers. So no conserved quantum numbers. And this dominates the total hadron-hadron cross sections as shown here. And there's been a lot of phenomenology of world data, and Donshi and Lansdorf worked on this for decades. And the latest fits suggested that this is still a competitive description, although there are others, where the intercept of this epsilon here of the Pomeron is 0.11, and the string tension is 0.165 inverse GB squared, which is lower from their earlier values. Now this picture,
plotting data, and the curve is that amplitude of that epsilon.
Yeah, so you're looking at the imaginary part of the forward scattering amplitude. Yeah, right, of course.
But
Yeah.
now, of course, that violates our sacred Poisson bound. So log squared also fits with two
Yes.
parameters
Yes.
equally well. Is that
Yes.
correct?
Yes, that's what I meant by the other descriptions. I'll come back to that towards the end of my talk. Discuss that.
So,
yeah.
how do you view this agreement? I mean, it can't be right, correct?
Yes. So that's the thrust of my talk, and so I sort of remind you about this particle remark as well. So this is just presenting a certain perspective, which is still powerful, but it has a lot of problems that are evident when you think about it. But nevertheless, it is still interesting to understand that it describes things like the shrinkage of the diffractive peak or several orders of magnitude. So there's a significant amount of data that it describes very well, but we know that there are problems, including alternative descriptions and bits of the data.
How does that value of the string tension compare to the string? How does that value of the string tension compare to other string tensions that we have, for example, from the spectrum of mesons?
Yeah, so this is comparable actually. So it's a comparable value. So the original value was 0.25 inverse GV squared, but this has kind of gone down since. So it's yeah. No, it's more. it's more than 10%. It's not that accurate. Yeah, that's.
I thought you mean the blue ball spectrum.
Yeah,
which is poorly measured.
Okay.
No, I mean
No. I think you mean this. You mean you're talking about, for example, this thing shown here. So if you have this fit, yeah. So this is this value, right? So yeah. That's shown here. Yeah, so this is a plot you also saw in the previous talk, this famous Jufracci plot. Again, for those who are unfamiliar, this is the mass squareds of meson trajectories, which have this linear trajectory as a function of the spin. And so you see this is obeyed not just by primary, but also sort of the daughter meson trajectories. As is well known, this has this very nice kind of interpretation in terms of the relativistic quark model as sort of a spinning string with a QQ bar, a string with a string tension. And there's been lattice work summarized here, which was you asked about. And so all of them, and here on the right-hand side are the so in addition to mesons, so you can look at hadronic scattering, and then there are these also, and this is a very complicated partial wave analysis to try and extract these masses with the spins. But there are some glue ball candidates, but these are still kind of uncertain as far as I understand, and sort of subject to this details of partial wave analysis. So there's no real absolute confirmation that the positive T continuation of the T-channel Pomeron exchange of these particular glue ball trajectories. So of course, this idea was very powerful, and it motivated string theory, as we know, and as well as sort of these kinds of relativistic quark models, which there's been a lot of work describing, and they do extremely well for a lot of these spectra in describing the data. So there's something very powerful there, as many people appreciate, but also there are clearly problems in terms of alternative descriptions, which are also equally successful. So yeah, so this is sort of the unsolved problem. What is a Pomeron in QCD? And so as Professor Groff's mentioned, that you immediately see that this is kind of problematic, because if you want this to sort of respect unitarity, the Froissart bound, and also by just looking at things like diffractive dissociation in experiments, that immediately suggests that there must be sort of multi-Pomeron dynamics occurring as well. So Pomeron, to look at diffractive dissociation, you need to have Pomeron interactions. And so that's kind of a problem. So now before we get there, so all the evidence suggests that, you know, when you go to high energies, that it's glue that dominates the cross sections. And this is kind of a nice parton model picture, where if you think of the hadron as some configuration of Alice quarks here, which we don't, some non-perturbative configuration, which is addressed by all these kind of weak partons that are in this cloud. But now when you boost the hadron to higher energies, these get time dilated. And so now if you probe it at very short resolutions, large Q squareds, then what you see is this very rapidly growing cross section. So these are structure functions as a function of the Yorkane X as you go to smaller X. And you see that the proton is overwhelmingly dominated by glue, and their accompanying C quarks kind of go along with them. And so this is immediately suggested that in thinking about the Pomeron, you have to, the dominant picture is gluodynamics. And in fact, the simplest picture of the Pomeron is that of color singlet two gluon exchange, while the orderon, so this has C parity 1, while its orderon C equal to -1 partner has quantum numbers of 3 gluon exchange. And in fact, it's the difference between the Pomeron and the orderon, which was conjectured by Pomeranchuk. So this is the Pomeranchuk theorem, as being responsible for the differences in P plus proton-proton and proton-antiproton cross sections, which should sort of go away at very high center mass energies logarithmically. And so here's sort of some data. So this is the differential cross section in T as a function of T. And so this was a basis that's been measured now from Totem at the LHC. So it's this very far detector at the LHC. And so it's a combination of proton-proton data from Totem as well as the D0 PP bar data at 1.96 DeV. When the former is extrapolated down to the lower energies of the tevatron, you find that there's this kind of difference between the lowest point in d sigma dt of the spectrum at the tevatron and then that at the LHC, I mean, that extrapolated down. So this is the difference between PP and PP bar at the fixed T. And this is claimed as evidence. So this is about a 3 sigma effect which when combined with independent analysis of the totem data at the highest energies, suggests that it's a 5 to 6 sigma kind of effect. And so this is claimed by this collaboration as a discovery. Now, this is again disputed. There are other alternative explanations of this, so I don't know what the latest status is in terms of there's a convergence on that. But anyway, so this is the status in terms of the Autoron. Yeah.
Autoron, I mean, is there evidence the Autoron disappears as you go to higher and higher energy?
Yeah, so its intercept is actually fixed. So it's at least in perturbative QC doesn't grow with energy, and there's some suggestions that maybe slightly below 1. So it should, but it's not a rapid decrease with energy. So now, what about the Pomeron now in perturbative QCD? And so this is the famed BFKL Pomeron. And so the way you construct this, it's a remarkable construction where you think about computing very high energy 2 to n scattering. And so here's some parton with gluon with large 4 momentum PA, PB, and you produce n of these partons in the final state, with momentum transfers going down Q1 to Qn plus 1 going down this ladder here. And you can construct all the invariants for this amplitude, and in a particular multi-Regge limit where you have strong ordering in the x values as you go down the ladder, or in other words, as the energies of these sub ladders here, you find that there's kind of a beautiful result. But before I get there, let me mention that you can also express this in terms of the momentum transfer and the center mass energies of each of these sub ladders. You can write these in terms of their transverse momentum and their x values. And this multi-Regge kinematics can be understood as a strong ordering in rapidity or in x. So you have the KTs are roughly the same along the ladder, the transverse momentum, but there's a strong ordering in rapidity, where rapidity is a log of each rapidity here by y is a log of the ratio of the rapidities between 2 successive such blocks here. And so let me go through briefly in terms of how this beautiful construction is kind of put through. And so there are 2 elements. So if you consider each sort of these building blocks here as a 2 to 3 process in sort of real radiation, then there are many different possibilities you can either emit the gluon from the middle, you can emit it from the top or the bottom. And using the Jacobi identity, what Lipato showed is that you can write this in terms of an effective vertex, which is called the Lipato vertex. It's non-local as a function of these variables here. The momentum transfers down this ladder, but it's gauge invariant. It satisfies the Ward identity. And so just on this basis here, you can write down this 2 to 3 amplitude just for this block here as an overall flux factor, 1/T, the momentum transfer, the propagator along the T channel, this vertex here, and then the other propagator T2. So now you can say, okay, now you can look at the virtual corrections to this 2 to 2 scattering. And so there you have this one loop here, and then you have the cross diagram, and you can write this as an effective propagator, where you promote 1/T. When you do this one loop calculation, you get log of S/T. So you get this large log because T is much smaller than S. But then you also get this factor alpha of T, which is infrared divergence. It depends on some cutoff scale here. And so this double log structure is sometimes called a Sukov form factor. Now, the Reggeization ansatz, which is widely used in sort of this physics, is that you can sort of sum up all of these n sort of ladders here. And effectively, what you're doing is then you're promoting this one gluon exchange to that of one where you exponentiate this one loop corrections here. So these are now logs of rapidity. You can write log of S of t in each of these subblocks is the difference of the rapidities times this this radial trajectory here. It's alpha of t1. And so the remarkable thing is that this object you can see you'll see is something that also has exactly the same properties as that of the bare gluon. The spin 1 exchange T channel, which has this kind of structure here. Now this trajectory alpha has been computed to 2 loops. This is the result here. And so it depends on both this kind of cusp anomalous dimension, the 2-loop cusp anomalous dimension of Wilson, of Wilson lines. And then there's also the 2-loop wedge anomalous dimension that contributes, and beta naught is the usual QCD beta function here, and zeta is a Riemann constant. So with this kind of construction, then you can construct the entire ladder. So I just focused on one building block. But then now you can put together the entire ladder. And so you have these 2 radioized gluons in the T channel, which have these effective vertices, these Lepato vertices. And so the Pomeron can be thought of as sort of the compound color singlet state of 2 such radioized gluons. And now if you look at the imaginary part of this amplitude, just from the discussion I had previously, you can understand there's a phase space factors, which corresponds to the rapidities and the momentum transfers. There's the radioized propagators on both sides of the cut, so 1/t times these exponentials. And then you have the product of these Lepato vertices, okay, which you get. So this is just a Feynman diagram calculation in this multi-radial kinematics of these 2-to-n process. And it turns out then if you go to the Mellon space, it has this very nice kind of structure where this object in Mellon space satisfies this integral equation, where the BFKL Hamiltonian is this object here, which can be written as this eigenvalue equation, which you can then solve and then do the inverse Mellon transform to compute this total cross section, which could then goes as S to some power lambda, where lambda is this BFKL intercept. And so you see right away that even for very small couplings, this is a very large interceptor. So remember the Donachie-Landshoff intercept was on the order of 0.1. So this is really much larger, much faster growth of the cross section. So this strongly violates the Froissart bound. Now, as I will discuss, the resummed BFKL, which includes going to higher orders, lowers this intercept to 0.3, but still the perturbative Pomeron is much faster growth than what you see non-perturbative. So there's a tremendous amount of work going on in trying to understand such amplitudes in the radial limit, starting with the next to leading log BFKL equation, which was first derived about 20 years ago. And so the way one sort of thinks about this is in going beyond the construction that I mentioned, is that now you are at next to leading log, you're resumming. So I missed an alpha, there's an alpha log S over T to the N. So you're including terms that are not ordered in rapidity. So you can have 2 gluons being emitted now from this vertex here. So that's one sort of correction. You can have 1 loop corrections to the Lepato vertex. And then you can have also these 2 loop corrections to the radial trajectory that I mentioned earlier. So all of these then sort of contribute. And that's what's involved in the construction of the next to leading log BFKL kernel. And as I mentioned, if you do appropriate resummations and so on, you find further that this intercept is the lower one around 0.3, which is consistent with data at large Q squared from Hera, but it's definitely doesn't agree with total cross sections. So there's of course since then there's tremendous continuing work on understanding the multi-radial limit of planar SUSY, so n equal to 4. And this is something that people in this audience have contributed greatly to in trying to understand sort of this duality between amplitudes and minimal area surfaces, close like polygon boundaries. And there's very rich mathematics on dual conformal transformations, so-called BDS, Bern-Dixon, Smirnov ansatz. And there's a very rich mathematical structure of these maximally Hessian violating amplitudes in the multi-Regge kinematics limit. And there's a really beautiful review of the state of the art by Vittorio Del Duca and Lance Dixon. I would recommend to anyone who's interested in the state of the art. This is very recent. Now, despite all this very beautiful work on the BFKL, this has an essential problem, which is that firstly, you find that the BFKL solution doesn't respect the conditions that you first impose on it, that you have some fixed large transfer momentum where you can use recoupling. When you solve the equation, you find that it has this infrared diffusion going on into the infrared and into the UV, and that does not, it's not cured by these next to leading log sort of analyses. And so that signals kind of a breakdown of the OP, and you further see that when you have this very rapid growth, when you produce a large number n of final states, soft partons, that leads to parton novel many-body gluodynamics. So in other words, when you have this ladder of these soft gluons which are being emitted in some order in rapidity, this multi-Regge kinematics, you find that at sufficiently high energies, it's competitive for these two soft gluons to recombine into a harder gluon. And then you can have such kind of screening cuts in addition, which are also beginning to contribute. So naively, these are power suppressed. But when you go to very high energies, the gluon densities grow very rapidly. And so these become comparable to the leading twist growth in the parton distributions. So if you just say, when does this equate with the leading twist DGLAP growth or BFKL growth, you find that this is for an occupancy, which is of order 1 over alpha. So this suggests that maybe there's a different paradigm in thinking about this problem, in the sense that what we're really seeing is emergence of classical dynamics when you go to very high occupancies at fixed resolutions. And so I should mention that in addition to this T-channel kind of BFKL construction, there's an alternative construction by Al Mueller, which is kind of an S-channel, where you think about this in coordinate space as opposed to momentum space, where you think of a dipole that's being boosted to higher and higher energies, and these produces these daughter dipoles, which are sort of reflected here. Alternatively, you can think of this picture where you have, say, this virtual photon which fluctuates into a quark-antiquark pair of a certain radius, and then the target is being boosted towards it, which contains a large number of these softer gluons. So this phenomenon is kind of represented in this kind of cartoon where I plot boosts on the y-axis, so that's logs in x or energy, as versus resolution. So this I inverted the earlier plot that I showed you. So when you go to larger q squareds at fixed boost, so you're probing the proton at finer scales, you see that you have these very small partons, and that's why the parton model works really well. So, there's no many body dynamics that you have to worry about. These are quasi-particles. However, if you go in the other regime, the Regge limit, you fix q squared and you go to higher and higher energies, smaller x, you see that because you fixed resolution, these objects are roughly the same size, and at some point they begin to overlap. There's close packing and screening that begins to occur. And so for each q squared, there's an x at which this close packing will occur. And this can be understood as emergence of a close packing scale, which is sometimes called the saturation scale. And so if you think about, say, this dipole scattering, then you can parameterize this kind of structure in this following way, where for a given dipole of size r perp, there's this emergent scale which grows with energy. And so for even if you have a very small dipole at very high energies, this QS is large enough so that the cross section becomes black. And so in sort of the old lore, nuclear physics, this is understood as kind of the color opacity, the black disk limit, where the cross section is sort of going as the volume grows as the area of the nucleus. as opposed to in the perturbative QC limit for smaller values in QS, when this is product is much less than 1, it goes as the volume. So this is the usual picture of shadowing reinterpreted in this way here. So you can understand this in an effective field theory framework, which kind of builds in this classicalization idea. But the basis is very general, is that if you think of a hadron moving at very fast or very high energies, then there's a natural separation of time scales between the modes corresponding to the fast partons, so the valence partons, and then the wee partons, which are these small x gluons. And on the light front, you can think about these objects as static modes, so large x parton static modes, and these are some color source distributions, which are represented here by rho A. And then the at very high energies, dipole scatters of these wee partons, which are fully dynamical gauge fields. So this is fully dynamical QCD. Because of this time separation, there's a natural separation of the dynamics of the modes, which are static, so that can be represented by some non-perturbative gauge invariant functional at some initial scale, which separates the two, the sources and fields. And then you can write down the full action for this. So this includes the Yang-Mills action plus a gauge invariant coupling of these sources and fields with some external sources to construct, all the operators of interest. Now, for a large nucleus, you can show that these are nothing but this gauge invariant functional is nothing but these quadratic and cubic Casimers, which actually can be interpreted in terms of these Pomeron and Orderon degrees of freedom, where these rows playing the role of these Reggeons that I mentioned earlier. And you can construct the saddle point of this effective action, and it's nothing but the non-abelian Widespread-Williams field. And in this explicit construction, you see how this emerging scalar arises, and it grows with the size of the nucleus. So I don't have time to go into this. So the formalism is really that of Katkowski's rules and strong fields. So you have strong fields, which then spit out these partons. So this is shown for flat cubes, where you're connected vacuum to vacuum graphs. And the formalism is this in formalism, the Schwinger-Keldysh formalism, where you represent propagators with plus sources and vertices and sources on one side of the contour and minus on the other. And so this gives you a very simple understanding of this old lore of so-called AGK cutting rules as merely the combinatorics of cut and uncut subgraphs contributing to a given multiplicity in this kind of picture of QFT in strong fields. And you can further show that there's a kind of RG that occurs where you remember I had this scale separating sources and fields, which is random. By requiring invariance of observables under the change of scale, you get an RG equation, which can be represented this way for an arbitrary operator at small x. In terms of the evolution of the rapidity, which you can think of as time, in the functional space of these source distributions at larger values of x. And this object is kind of diffusion coefficient, which is a retarded Green's function of gluons in the strong background field. And so this describes, since it's a Fokker-Planck type equation, it describes a Langevin diffusion of the fuzz of weak partons in this functional space. And you can construct kind of a general hierarchy for endpoint Wilson line correlators, which actually to leading logarithmic accuracy, you can solve numerically exactly. But it's the state of the art is next to leading log. And so now if you think about this dipole picture here that I mentioned earlier, then the scattering is off some kind of a shock wave, which is this classical solution, but then you can construct loop corrections inside this background. And it turns out that for this dipole correlator Wilson lines, which is this closed loop here, which includes Wilson line at some point x and some Wilson, it's conjugated some y. This describes following nonlinear equation of this form here. And this is nothing but the BFKL kernel you see here. And so when you have this one loop emission, the Z perf corresponds to the position of the emitted daughter dipole. Now, if you take the large NC limit and you choose initial conditions, which are large nucleus, this nonlinear term here factorizes. So you can write down the expectation value of the product of traces as a product of expectation values, and you get a nonlinear equation, nice closed form nonlinear equation that's called the Bolesky-Kovtchagov equation. And it has some very interesting properties which are very similar to that of the FKPP equation in statistical mechanics. And what you see is that this cross section, which at this high occupancy state, saturates solution saturates a cross section for fixed impact parameter. And so that this nonlinear picture corresponds to all these kinds of multi-Pomeron kind of objects which kind of merge to meet this dipole, which is not shown here. And the BFKL equation is nothing but the low density limit of this nonlinear equation. So that's kind of, so if you think about BFKL, it's a limit of this framework. But this is much richer. It's also a picture for endpoint correlators beyond the 2-point correlators, Wilson lines described by BFKL. So on to phenomenology. So there's a lot of phenomenology with this framework for the last several years, which are now at next to leading or next to leading log accuracy in this CGC EFT. So this fits to data with the same kind of parameters that fit inclusive distributions at the LHC as for different rapidity windows as function of PT. There are, of course, a number of assumptions about confining dynamics, impact parameter dependence, and so on that go on in such fits, but they are common to also other perturbative QCD descriptions of data colliders. So that's sort of the essential feature of our ignorance of confining dynamics. Now, this framework is also has another great source of power, which is that if you think about, say, okay, you have Pomerons, how are you going to describe the collisions of two nuclei at very high energies? So you have all these many particles producing this iconic image from the star collider at RIC, these 1,000 particles or so. How do you understand this in some kind of ab initio way? However, in this effective description at very high energies, what you have is a collision of two gluon shockwaves and fluctuations around those. And you can actually follow this all the way, this picture here, we compute the collision of these shock waves and look at fluctuations around those. And there's a very similar dynamics that's similar to what's described in sort of literature, black hole collisions or in gravitational collisions in terms of things like the butterfly effect and scrambling and so on. You have non-thermal attractors being formed as part of this evolution, which you can understand. And eventually you see that you form a quark-gluon plasma. So this framework allows you to compute at very high energies the emergence of a quark-gluon plasma. In fact, you can show that a bath of soft gluons emerges at some scale that's parametrically given the powers of 1 of this close packing scale, and you can compute the thermalization temperature. There are coefficients which are uncertain. But what this tells you is that if you go to sufficiently high energies, as the close packing scale goes to infinity, thermalization is almost instantaneous. And so one of the goals is, sorry, I'm running out of time, is to uncover the early time dynamics of this physics here. So this is kind of one of my last slides. So back to the Pomeron. It's always there in the background, even if you're trying to go away from it. And this is the question that Professor Gross asked about, alternative descriptions and also what's the relevant scale. So one way to think about this is that even though this effective field theory construction is very useful for describing states with, say, high multiplicities, particular final states at fixed impact parameter. However, as you go to higher impact parameters, you see that this kind of black disk region, screen region, is surrounded by then the parton regime, which then eventually is this pion cloud. And this is something that we don't understand fundamentally, how these transitions take place between these, and how does a proton grow logarithmically as you go to higher and higher energies. And this is how I would formulate, at least my simple way of formulating this outstanding problem, is that, if you just look at this BFKL kind of dynamics, the kernel contains a Coulomb tail, which is what is responsible for violating the Frossard bound. And it's unsurprising because the latter requires existence of that. So this is the outstanding question, is how do you map this to physics at larger impact parameters? So it's trying to focus the problem a little bit more. And this is a question that Professor Gross raised. in some discussions we had in collaboration is what sets the scale of Rosat bound. And so fits to data is, and these are some of the fits that are shown with this log squared kind of dependence that we discuss, that the scale is about not the pion mass, but it's about 10 times pion mass, which is consistent with sort of the lightest gluon mass or the chiral scale. And there's also this question of what happens to chiral limit. And if you're interested, there's a nice discussion by Shmuel Musanov quite some time ago on this. So this is my final slide. I apologize. This is the landscape now, and so I've tried to identify in my kind of way of thinking about it, what the outstanding problem is in our understanding, and you know, how do we kind of go along this trajectory here, and how can we bring sort of lattice QCD in these EFT methods, as well as sort of the EFT of long strings to kind of make progress on better defining this, at least this outstanding problem. And so there's precision studies of the Pomeron and the EIC that will take place. So you can do deep elastic scattering and measure the structure of the Pomeron. The EIC will have 1,000 times the luminosity of Hera, so you can have very clean differential studies of such color singlet exchanges. You can look at hard jets that probe the structure here. And you can also do some studies for large nuclei. So thank you very much, and I apologize.
That's very, very interesting talk. Just a question, since
Right.
we talk a lot about this large and
Right.
QCD string. Say if you consider scattering of mesons, right, there is this non-planar channel
Right.
with a closed string exchange. That's basically one way to think of the Pomeron. No?
Yes, yeah.
Because here
yeah,
you're talking
yeah,
about baryon scattering, but
Right.
if you just look at perturbative meson scattering,
Right. Yeah, I believe so. But you know, a lot of this small x dynamics at sufficiently small x is universal. So it's if you go to sufficiently small x, the dynamics is purely controlled by glue. Of course, the initial conditions matter, but if you go to sufficiently small x, the physics, there's a universal aspect to the physics that emerges, and that's independent of whether you're boosting a meson or a baryon. So that's the interesting
questions.
Yeah, this really isn't necessarily for you, but just we just heard a lot about incredibly precise lattice data, which allow us to calculate mass and matrix. But notoriously, we don't know how to use numerical lattice techniques for scattering. Have you thought of, or has anyone thought about how we might do that, and whether quantum computers could help?
Yeah, so I think that's the stock answer is quantum computers, and we are really looking at the very deep Minkowski regime here, even at very small x, where even the OPE, as I've argued, sort of breaks down completely. So the usual moment analysis of structure functions is really problematic. So I think it really requires a new idea, and I think that would be something that that is worth pursuing if one is ambitious enough. Quantum computing, of course, is the standard answer if you have the Hamiltonian framework. Now, one of the issues that I am concerned about is that if you think about this as a light front Hamiltonian, so if you think about the Hamiltonian at light front, then there's the light front Hamiltonian is non-local, and it has zero modes that again kind of bring you back to these issues. So even if you were to say, okay, we can construct a Hamiltonian and solve it on a quantum computer, one has to still address these issues about the non-locality of this Hamiltonian. So it is an outstanding problem.
And more questions.
Which is the reason to work on it.
Okay, let's thank Raju again.